शुरू करें जनाब फिर. Okay. Morning everybody. Subh khair. So we were talking about the constant coefficient homogeneous second order differential equations, linear second order differential equations last time. So just to say one thing, that if you have this kind of an equation, okay, so let's say we are writing down the constant coefficient equations. And I'm writing down a homogeneous. There are two special cases. So if I get rid of this first order derivative, so I can have two special cases. One is this and the other is this. So these are the two most well-known second order differential equations. This one you must have realized by now is the simple harmonic oscillator equation, and this is the other equation with the minus sign. And what is the major difference? Sorry? So you need to talk on the mic because guys then complain, that they can't hear what you.
एक में एक्सपोनेंशियल्स आएंगे और एक में सिनुसॉइड्स और कोसाइन्स आएंगे.
So which one you think will be composed of sines and cosines?
The first one is going to be sines and cosines, and the second one is going to be.
So if I ask you, without jotting anything down on a piece of paper, and just tell me what is the auxiliary equation for it, so what will be the auxiliary equation for it?
M squared plus k squared
Yep.
equals.
So it will be, in this case, it will be m is equal to plus minus iota k, and in this case it will be plus minus k. So this will be a e raised to power iota kx plus b e raised to power minus iota kx, and in this case you will have a1 e raised to power kx plus b1 e raised to power minus kx. So this is an oscillatory behavior, and this is an exponentially growing or decaying behavior. Okay. So let's say this kind of behavior is there. So you have an exponentially growing situation. So what do you say if you come up with this kind of a solution? So there are many. So because you guys have, some of you have done your undergrad, some of you are doing your undergrad. So have you come across a situation where you write down this kind of an equation, and although it is a perfectly legitimate solution because it's a second order differential equation and it has two solutions, but using some physical considerations, can you drop any term here? So we can, at times we say this is growing infinitely, and let's say something is away from the source, so you can't say it will grow on forever, so you will just drop it. So for instance, in plasmas, you come up with this equation, and purely on these grounds that something cannot grow forever, you drop this term and you get this expression of shielding.
Sir, but it depends on the conditions given, right?
Yep, yeah, exactly. So it depends on the physical. This is a solution, but then whatever system you have before you, then you can make certain assumptions. So it is not that always when you write down an equation, and then there's another mistake that students make. So what do you think, if this thing goes to infinity, what happens?
Continuity breaks.
No, but what happens to this function at infinity? So let's say you are looking at a cos function and a sine function. It will oscillate forever. Yeah. So some people say that it will go to this and that, but nothing happens to it. It will go on forever. This is an exponentially growing and decaying function. So for instance, if you write down the equations for the electromagnetism. So over there you get actually both these combinations. So anybody can tell why? No, but why do I get a product of an oscillatory function and an exponentially growing or decaying function? No, why do I get it? Do I need to make any assumption to do that, or I will get it naturally?
Sir, we do get it naturally, but then we see
Now, what do you
like our
what do you
conditions.
assume? So this is the exponential e raised per iota k dot r minus omega t that you assume. So where do you get something which is exponentially decaying or exponentially growing? Absolutely. So unless you assume that omega is complex or k is complex, you can never get it. So for when you take omega complex, you will have something which is growing or decaying in time. And if you have k complex, then you will have something which is spatially growing or decaying. So that is called the spatial damping, and the other is called the temporal damping. So these are the things that you need to be aware of and mindful of. So I have dropped one important term here to get to this basic stuff, right? So when you have a damped harmonic oscillator or something like that, then of course you can't do that, okay? So what happens then? So we will talk about it, but first I need to tell you a bit about the non-homogeneous equations, and then we will talk about it. Non-homogeneous equation. Again, when I say non-homogeneous, it is assumed that this is non-homogeneous linear second order first degree differential equation. Classification should always be in your mind. So I can write this as and if I write this thing in standard form, then I will have this is the equation now that I have. Okay. So when I try and solve this equation, what is the primary objective? What is it that I'm trying to find? Y. So as I told you, Y is the, in physics, Y is called the response of the system. So let's say when you write down this thing and you get something like this, what do you call this response? Natural response of a system. Okay? So those of you who are not familiar with this terminology, you should acquaint yourself with this, because this is what it means. There is nothing on the right hand side. So this is the natural response of the system. You displace a pendulum, you leave it, and it oscillates. That's what we call the natural response of the system. So if you have something on the right hand side, then it means this is the way you have fiddled with the system. Okay? That is called the input. And I have to show you today that in this particular case, the theorem is that YC plus YP is the total response of the system, where this YC means the natural response and YP means response to the input, and total response is like this. But how can I say this? Okay. So the theorem is very simple. The proof is, of course, very simple. That you just assume. So I guess you guys know that I can write this thing as L of y is equal to, let's say, f of x, where L is equal to right? Is that okay? So in the homogeneous case, how would I write this equation? Ly is equal to 0. Okay. So now let's say that some capital Y and Yp are the two solutions of the input, okay? And you write this as y minus yp. I assume that these are the two solutions to whatever input I am using, and I say that I define this u as y minus yp, and now I apply L of u, so that will be L of y minus yp, and using the linearity property I will have L of y minus L of yp. So both are the solutions of the this equation. So this will be yp minus yp, and this is equal to 0. Because in fact you can say, let's say, you can also say f of x minus f of x. But the interesting part is that you write like this. You don't write like y plus yp, and in that case you won't be able to cancel it. And most importantly, once you do that, then what you get is L of u is equal to 0, which means it's a homogeneous equation now, and you know what the solution of the homogeneous equation is. What is it? Let me write it here. This will be u is equal to c1y1 plus c2 y2, and your y will be equal to c1y1 plus c2 y2 plus yp. So that's how you know that this solution works. Similarly, if you have yp1, yp2, so you can show that they will, you will use, let's say, let's say it is g some, well, f1x plus f2x. So if you write two yp's like yp1 plus yp2, it will give you f1 of x plus f2 of x, and you know that is how you need to deal with it, that they can be treated independently. If you have, but when you write something like this, it means that this is the total input. Although you can divide it using the linear combination, but in principle the problem that is given to you is this. You need to calculate the response of the system for these two inputs, which you can find out either by considering them as one or by considering this and considering this using the linear superposition principle, right? So that is something that I wanted to show. Questions here, please ask, else I'll move forward. Are you okay with it? Now there are two ways that you can find the solution of a non-homogeneous second order linear differential equation. One is the method of undetermined coefficients, and the other is the variation of parameters method. So there is sometimes we can confuse something. Last time we did something which we call as reduction of order. So in that we use y as u of x y. So that is also a variation of parameters, but the real variation of parameters is when you have a non-homogeneous equation and you write down your solution. I mean, you want to find out something like this. So over there you have two So we will come to this, but at the moment I want to say a few things about. I'm not going to do it because of the paucity of time, and then because we have a most general method, so I will want to discuss that in full glory. But for this method, for any constant coefficient equation, you will use e raised to power mx, you find the auxiliary equation and find the solution. But for certain inputs like x square, like cosine of x, sine of x, e raised to power x, even for I mean, this is a polynomial, you can solve it for a polynomial, no problem at all. You have certain inputs and they work for this method because you take the first derivative, the second derivative, and plug it back in the original equation, compare the coefficients, and you find the answer, and you write down the solution using y is equal to yc plus yp. Cosine x will give you sine x will give you cosine of x, e raised to power x, no matter what you write, you will get e raised to power x. So all these inputs work, and in many physical situations of interest, you actually come across these kind of inputs. So you can use method of undetermined coefficients, but for log of x, 1 over x squared, you see secant square x, tangent x, and so many other, sine inverse x, cosine inverse x, you can't use this method because these derivatives never reproduce themselves. So that is why the method fails here. So for those of you who have anybody who has never come across, so Ahmed is not here, so I don't think there is anybody amongst you who has never come across method of undetermined coefficients. Have you? So anybody can tell me about the glitch in the method? Aapne, you don't know, somebody else. You? Can you please give him the mic? Give her the mic actually. Ji madam. Any idea?
No sir.
Did anybody teach you this method?
Yeah, but I forgot.
You forgot, okay. So what happens is that, let's say if you have a solution yc is equal to c1 e raised to power x plus c2 e raised to power 2x, and let's say the equation that you are given over here is y double dash plus p of x y dash plus q of x y is equal to e raised to power x or e raised to power 2x. So if you try and use this method, then you will find that you will not get any answer. So the problem is that if the solution of the homogeneous equation contains the same function that you get in the input, then you will not get any answer. So you will have to multiply it with x to resolve that problem. And let's say if you have some x here, then you will have to multiply it with x squared to solve that problem. So that's another glitch in the method, that if you write down an input term here which is also there in the natural response, then of course the method fails and you have to do something about it so that you can solve it. So there are many caveats in this method, and most importantly that any arbitrary input cannot be entertained within the domain of this particular method. Okay? Good? Questions? All right, so if everything is clear, then let's go to the method that I would like to talk about, and that is method of variation of parameters. That's the most general method. The only problem with this method is that you need to know the solutions of the associated homogeneous part. If you do not know the solutions of the homogeneous part, then of course you can't solve this method. Otherwise, any input can be used. So let's begin. Method of So good thing about reading a book is that she will tell you something beforehand, and then once you get the answer, then you can see for yourself why what somebody said is correct, because the answer should show you the limitation which has been initially discussed. All right, so let me go and now talk about that. Okay, here we go. Method of variation of parameters. So I need to find out, so assuming that I know what the solution of the associated homogeneous part, my task is to find now the particular solution. That is the task before me. Would you like to tell me what is y1 and what is y2? These are the solutions of the associated homogeneous part. It's a second order differential equation and it will have two solutions. So let y1 and y2 are the two solutions of the associated homogeneous part. Then, just like we solved the problem for the first order differential equation, over here because we have got two solutions, I have got two parameters. So madam, what is the objective here now? What is it that I need to find in order to determine the particular solution?
We need to find the homogeneous solution first.
We assume that we know the solution. We are not going to bother ourselves with
find u1 of x and u2 of x.
u2 of x. So these are, so that is why these are the variation, this is the variation of parameters method, and these are the two parameters that we need to find. Okay? So the equation before you is what? Y double dash in standard form plus p of x y dash plus q of x y is equal to y p, and yp you have of course assumed to be this is not yp, I mean let's say it's called f of x. So we have to find this solution. So what do you need to do? Take the first derivative, take the second derivative, plug it back in this equation and see what we get. So what is the anticipation here? Once I do that, so what do you think will happen here? So I'm just asking you because I need to know, what do you anticipate? That once you plug in the values and you have two unknowns, what is essentially that you want? Two equations. So I need to have two equations so that I can have the requisite, equations to solve, because it will be a completely determined system. I will have two equations, two unknowns. Go ahead. Do a little bit of algebra. I'll write it for you, but you also need to do it because this is important for you to see for yourself certain things. Have a look and see whether I have missed anything or I have written down all the terms. So how many terms he has written? 3 and 5 and 8. Okay. Two, three, four, 5, 6, 7. G? Thank you. Yeah. So one thing that now that we have done this thing many times, you should immediately anticipate that there will be a term which will be y1 double dash plus pxy1 dash plus q of xy1, which will be equal to 0, because that is a solution of the associated homogeneous part. And similarly you will have y2 double dash plus p of x y2 dash plus q of x y2, which will be equal to 0. And once I am done with all that, then let me write down what I am left with. This is already there, but let me draw the line here. So I will have d by dx u1 dash y1 plus d by dx u2 dash y2 plus p of u1 dash y1 plus u2 dash y2 plus y1 dash u1 dash plus y2 dash u2 dash. And this will all be equal to f of x, and I can write this as d by dx u1 dash y1 plus u2 dash y2 plus p u1 dash y1 plus u2 dash y2 plus y1 dash u1 dash plus y2 dash u2 dash is equal to f of x. Can you see similar terms here? So as you can see, this term and this term, these two terms are similar, and the other equation is this one because it contains y1 dash u1 dash. Over here it's u1 dash y1. So the two equations that I want to get are, I can plug this to be 0, and what I am left with is this equation. So I have two equations, u1 dash y1 plus u2 dash y2 is equal to 0, and I will have u1 dash y1 dash plus u2 dash y2 dash is equal to f of x. So these are the two conditions. This condition I impose and the other one I am left with. The objective right from the beginning was to find out two equations to find out the two unknowns. So once I did my algebra right, this is the equation that I got. We forced the condition that this ought to be 0, and then what we are left with this. So I have got two. So although this is in u1 dash and u2 dash, but this is actually what I want. Okay, these are my two unknowns. I take the antiderivative and I will get u1 and u2. But now if I have something like this, do you know any method from where I can solve this? So Kramer's rule is the one where you can find out. So I'm just writing down the solution. So what I will get is u1 dash is equal to w1 over w, which is equal to minus y2 f of x over w, where w is our friend Wronskian. u2 dash is equal to w2 over w, which is y1 f of x over w, and so this is okay. So w is my well-known friend y1 y2 y1 dash y2 dash. So if you do Kramer's rule, it's a matter of 5 minutes. You will find out that w1 will be equal to 0 y2 f of x y2 dash, and w2 is equal to y1 0 y1 dash f of x, and that's it. So now you can immediately realize why initially it was said that unless you know the associated homogeneous part, you will never be able to find the particular solution, because everything here involves y1 and y2. And if y1 and y2 are not known, you cannot know anything. Okay? So it's always a good idea to do an example, which we are going to do, but up till now, if you have any questions, yeah. If you please take the mic and ask, then the friends watching us live would be benefited.
सर यहाँ पे p वाली टर्म कहाँ गई है?
Which one?
ये इस पार्ट में where the p u1 prime v1 y1 plus u2 prime v y2.
So we impose the condition that this thing ought to be 0. So when once it is 0, so 0 multiplied by anything is 0. So I am left with this thing, and if these two are 0, then I am left with this thing.
और सर वहाँ से जो qx वाली टर्म थी वो इधर क्यों नहीं आई?
Because y1 double dash plus p of x y1 dash plus q of x y1 is equal to 0, y2 double dash plus p of x y2 plus q of x y2 is equal to 0. Everything is done and dealt with. Yeah, good. But you have asked this is very good. Yeah, I'm glad that you're asking these questions, because you see, this is the disadvantage of doing the algebra and the advantage of doing algebra. Had I not done the algebra, I would have been at sea right now. So because I have done it and many times over, so I know. So even at the cost of repetition, I would say that the only way to learn mathematics is to do it, just like any other thing. Good? We are good here? And now the best thing about this is you give any input and it will solve it for you. It doesn't demand something to have a repeating derivative or anything like that. But everything depends on the solution of the associated homogeneous part. So we will do an example so that we don't waste a lot of time doing it. I'll write down the solution of the associated homogeneous part straight away so that you don't. So the example is y double dash minus 4y dash plus 4y is equal to x plus 1 e raised to power 2x. So as you can figure it out, these are repeated roots, and the solution that I will have will be yc's will be equal to c1 e raised to power 2x plus c2 x e raised to power 2x. So you have your y1 and y2 with you now, and what you need to do is to find u1 and u2. Once you find u1 dash and u2 dash using this, then you can just take the antiderivative and you will have u1 and u2, and you will apply it here. And you will get the answer. Okay, go ahead, do it. Just to familiarize yourself with these W's. The original W is the Wronskian. W1 and W2 are the variants, right? That's the direct consequence of applying the Cramer's rule. Anybody would like to tell me what W is? E raised to power 4x. Not equal to 0. So the linear independence of the two solutions is demonstrated here. That is the requirement. And if it goes to 0, then the method doesn't work. So you need to find two solutions which are linearly independent, of course. Otherwise, we can't go anywhere. So those of our colleagues who say mathematics doesn't have any logic, the reason that I have managed to identify is that they never try and go through the method through which they can solve the problem. If you have been told that do this without being told how does this come about, then of course you will think that it has no logic, and it has come from somewhere and you just have to believe it. It is extremely essential because all of you who intend to become researchers and they will become eventually teachers, so they need to always tell the logic. Otherwise, students will not be able to appreciate it as science. There will be a lot of mysteriousness about it, that it has come from somewhere and they just have to accept it. That doesn't work in science. Humans have developed it, and humans have the capacity to show it. Some of us have the capacity to show it and to work those solutions out as well. Okay, W1, W2, anybody? All right. So it tells me that one is minus x plus 1 e raised to power 4x and the other is x into x plus 1 e raised to power 4x. You guys have got it? Anybody? Okay, and if you have, then just we have to G? Okay, thank you. Is that okay? Good. So again, because you have worked it out, that's why you know. Wonderful. So now once you are done with everything, so you will have u1 dash is equal to minus x square minus x. Okay. So what is it? This is du1 over dx is equal to minus x square minus x. So it means u1 is equal to all right. Similarly, for u2 dash, you will have x plus 1, and in that case, my u2 will be x square over 2 plus x plus c2. And now I can plug these two values in here, and I know what my yp is. Yc is already known, so the full solution is now known. So if you are given, initial values or a boundary values, then of course you can determine C1 and C2, and you can remove the arbitrariness here. All right. So that is all that you need to know about the method of variation of parameters. The only problem is that you need to know the solution of the associated homogeneous part. If you do that, then this method works for any kind of input. Questions, please ask, else I'll move forward. Right. Okay, so now a bit of physics.
Particular solution may be C1 or C2.
G?
U1 or U2 तो particular solution है. ये आखिर में YC के साथ absorb हो जाएंगे.
Yeah, of course, yeah. And in fact, if I have written in YC C1, C2, then I have to choose some other C over here, right? It has to be C3 or C4 or whatever. So this you should bear in mind, that how did we get this and what are the expressions of U1 prime, and you know what Wronskian is. So now let's talk about a physical problem. So this is, I'm going to write down differential equation of driven motion with damping. So the equation is this: m d2x over dt squared is equal to minus kx minus beta dx over dt plus some f of t. So what are the different cases that you have come across in the study of simple harmonic motion or mass spring systems? So you have a natural oscillation, then you have a damping, and then you have some forced motion, right? Some force that you, so in that case, so if I just rearrange it, divide everything by mass, so I can write this equation as Now that you have done everything when it comes to the second order linear homogeneous and non-homogeneous equations, so you can immediately see certain limiting cases of this particular equation. So the simplest form would be from here would be what? Saptan, please tell. Give him the mic. The simplest possible thing that you can get as a limiting case from here.
Sir, I'm not quite sure.
So let's say if I put the periodic force equal to 0 and I put this particular term 0, then what do I get? Simple harmonic motion, right?
Yes.
And if I put this equal to 0 and I write this thing down, then
And second order linear.
this is second order, yeah, this is second order linear differential equation, but now there is a first order derivative.
Yes.
So why it is called damn term, we will have a look at it, but the forcing term here is now the input. So your response will include the effect of this forcing term and which particular function you choose to. So again, if f of t is 1 over t squared, log of t, sine inverse t, you can't use method of undetermined coefficients. But if you have the exponential or a polynomial or you see a sine cosine, a periodic force, then of course the method works, the method of undetermined coefficient. It is as good as the other method. All right. So let's look at the, so now he says, so this is what I'm going to do. So in order to show you the physics and also certain concepts that involve some kind of investigation of the solution that you get. So he says, interpret and solve the initial value problem (1 by 5 d2x over dt squared plus 1.2 dx by dt plus 2x is equal to 5 cosine of 4t, x of 0 is half, x dash of 0 is equal to 0. Okay. So if you look at this equation, so you multiply throughout by 5. So what you get? Of course, you can associate this with, if you compare with this, so you can associate this with the mass. So it can be in slugs, it can be in kilograms, depending on which particular system of units you are following. So this is the equation that I have. All right. So I will not ask you to solve this because this you can solve both using the method of undetermined coefficients as well as the method of variation of parameters. But just find this for yourself so that you at least get an idea. Just write down the auxiliary equation, homogeneous part. You just put. So here it will be y is equal to what? Constant coefficients. What do you need to? Mx What will be the substitution here? GG. Independent variable is t here, not x. So this is one lesson. Just close your eyes and you start doing it without realizing that the variables have changed. Here is not going to work. So over there it was y and x. Over here it's x and t. So the substitution will be y is equal to e raised to power mt. So now tell me what is the solution of the associated homogeneous part is. So what is the auxiliary equation? So you will get xc of t is equal to e raised to power minus 3t c1 cosine of t plus c2 sine of t. Now you tell me, give him the mic. I need to ask you something. So you see two terms here. If you have to say, put it in words, what kind of complementary solution you have obtained, what will you say? I'm asking you, this is the solution of the associated homogeneous part, right?
Okay.
So if you have to put it in words, what kind of a solution you have obtained, what will you say?
Complex.
What makes it complex?
Because
Well, complex in a way, you say because cosines and sines are here, that
Yes.
makes you think that way, okay. But
the auxiliary
if
equation
you,
also had imaginary
if you look at
answers.
cosines and sines, so what is the
Simply
convention?
harmonic. I
These are
guess.
periodic terms, right?
Periodic, okay.
And what about the first term that is getting multiplied here?
First amplitude maybe
No. The function, how does it behave?
exponentially
How?
decaying. minus
Exponentially decaying. Okay, good, very good. Up now, give mic to that guy. Yeah, over there. Yeah. So, when you say damping term, what makes you say that? For instance, if I put dx over dt equals to 0 here, what will happen? Then what do you anticipate here?
The damping term goes to 0.
Yeah, so it will disappear.
Just oscillate it.
So this is the origin. So now in any physical system, when you have this first order derivative appearing, so your anticipation should be that you will be seeing a decaying term, right? It could be depending on the sign, you can also get an exponentially growing thing, but generally it's a damping term because there's a plus sign here. So these are the equations that you obtain. This is the equation written for a mass spring system. This is what you get. And then there is a force term also. You are applying a forcing term here. So this is what it is. And now I'm going to write down the final solution. And we will try and, but overall, if something is written like this, can you qualify it as a periodic force? So if there is no exponentially decaying term, then of course it's periodic. But in general, when you have such kind of thing, you will say it as non-periodic. Okay? So let me write down now the complete solution. So using the method of undetermined coefficients, if you have to solve 5 cosine of 4t, what does the particular solution looks like? How does it look like? Okay, so it means whatever you input, that kind of yp you will have. So you will have a periodic type of yp because yp is constructed from the input that you have. So that will surely be a periodic force. So my solution is, this is how I write down the complete solution, and that will be e raised to power minus 3t c1 cosine of t. In fact, if I just apply the initial values and I calculate the whole thing, I will get 38 by 51 cosine of t minus 86 over 51 sine of t minus 25 over 102 cosine of 4t plus 50 by 51 sine of 4t. This is the complete solution that I have. All right. There is one thing that I need to check, so maybe over there I need to correct myself if I have said it that way. So you correctly pointed out when you have to write down the yp, then I will not write down the constants, right? So the first thing that you learn from here is, so as you can see, this is your yc and this is your so your forcing term is independent of the initial value problem. Okay, because you will write down a cosine of 4t plus b sine of 4t, you will find out the a's and b's and you will plug in here. They have absolutely no relation with the initial value problem. So initial value problem will affect the natural response, because these were the ones where the C1 cosine of t and C2 sine of t appeared, and you have to calculate those, but these two had nothing to do with the initial value problem. So now I will just so certain things that he says. So first things first, the natural response is.
Excuse me, sir. Sir, in variation of parameter, we saw that the particular solution actually depends on the homogeneous solutions, right?
Yes.
So if we have our initial conditions in the homogeneous, so the particular solution actually depends on that indirectly.
Well, when you take the derivatives of things, so then constants all disappear.
All right.
You see, what did you write? You write down y is equal to yc plus yp. Your yp does not contain any c's. Your yc contains c's. And in order to compute those c's, you have to use the initial value problem.
Yes.
So it means what actually gets affected by that is the complementary part, not the particular part. Because what did you write? u1 dash is equal to minus x square minus x, u1 is equal to x cube over 3 plus x square over 2, you multiply it with your y1. Okay?
Oh, yes. Yes, okay, thank you.
Eventually it will be affected in that case, in the sense that your C1s and Y1s are your YP and YC, so I construct my YP as U of X Y1 plus U2 of X Y2. But if you look at just Y1 and just Y2, so that is in your case, the one we have done, it is e raised to power 2x and x e raised to power 2x. So there is no c appearing here. It's the yc that said the answer is c1 e raised to power 2x plus c2 x e raised to power 2x, and in order to determine yc you have to compute this. But over here this is just y1 and y2. No c. These are just the functions. Thank you very much for asking this question, because this is very important. So whether you apply the method of undetermined coefficients or method of variation of parameters, the complementary part needs the initial value conditions to compute the C's, but the particular solution is independent of that. It will have no bearing on. So similarly over here, these are the ones computed from the initial value, and this is the one which is not determined. Now, if you look at the long-term solution, how the system behaves in the long run, because it is a dynamical system. So what is the question that I will ask? What is the natural question to ask? Yeah, t goes to infinity. So what do you see here? So because this is e raised to power minus 3t, nothing happens here, of course. It will still be oscillatory, but this will be 1 over infinity and it will go to 0. So in mathematical terms, what we say is that this is a transient and this is the steady state. So the steady state solution over here would be due to the forcing term. And the natural, yeah, please. You have to ask. Please give him the mic, yeah.
ये हमारा डैम्प सिस्टम है ना, राइट?
Yes.
तो हमने कहा कि एस टी गोज ऑन द फर्स्ट टर्म गोज टू 0, फिर उसके बाद जाके ऑसिलेट करता रहेगा. तो फिजिकली ये चीज़ डैम्प तो नहीं हो रही, फिर भी चलती नहीं रह रही.
The question that we are asking is, we have got two terms, and if we put t goes to infinity, what vanishes and what stays? So this term goes to 0 means it vanishes. What stays with me is this particular term. So it means the complementary solution is the transient solution and the steady state solution comes from the forcing term. Yeah, because external periodic force you will continue to apply, right? You can also, anticipate it, because let's say if a pendulum is oscillating, just simple harmonic motion, because of air friction and all, it will eventually damp and it will come to rest. So this is what it says. This is a transient. But if you continue to push it, it will continue forever. But you will have to continue pushing, right? That's the whole idea. So this is a beautiful physical example where you can see the method working and also all the physics which is buried in here. Okay? Questions? Please ask. So in the same vein, you can also talk about so I will just write down an analogous equation.
सर इस केस में तो फिर वो रेस्ट में नहीं आएगा ना, मतलब जो उसकी मोशन है वो सॉर्ट ऑफ डिस्टर्बेंस से चली जाए, मतलब उससे डिस्टर्बेंस हट जाएगी जस्ट, क्योंकि वो एक स्टेडीली एक ऑसिलेटरी मोशन में आ जाएगी.
This is what is left. So it means this is the steady state. This is the solution that will prevail forever.
Yes.
Right? Because you are continuously pushing it.
Yes.
If you put f of t equals to 0, then it becomes 0. My anticipation for any physical system is that it will eventually come to rest if there is no force that is perturbing it all the time. If there is a perturbation that you create externally, then of course the motion will continue forever. But if you withdraw that force, you will get 0, and this is what you get. Right?
अगर डैम्प टर्म उसमें रहे और हम एक्सटर्नल फैक्टर्स को हटा दें तो फिर वो रेस्ट में आ जाएगा.
Yeah. Just like friction. So this is the friction term. I'm telling you, there is this pendulum which is oscillating. Because of the air friction, which is equivalent to that term over there, the damping term, it will eventually come to rest. And that is essentially what we means, that I will have y is equal to 0 or x is equal to 0. Right? But if I continue to slap it with some, or I just make some kind of external perturbation or external work, then of course it will go on forever. And that is what we get. But of course you need to have this physical picture in mind to understand that whatever solution you are getting makes physical sense. For any perturbation in a system, if it is not there, if there is no continuous perturbation, it will eventually die out. Away from its source, anything will die out. You know, gravitational force and all, if you go far away, you know, it becomes zero. R goes to infinity, you know, 1 over infinity, this becomes zero, right? That is our anticipation, away from the source. So this is an external periodic force. And if it goes to zero, then everything becomes zero. Yeah, please. You good? Please ask. Okay, so now we will talk about the Green's function for the second order linear homogeneous, not non-homogeneous differential equation, because Green's function, by the way, does not work for for homogeneous differential equations. So be it PDEs or ODEs, it works for non-homogeneous systems. That's the way they are constructed. How they are constructed, we will see over here. We will see how it comes about for the ordinary differential equations. Okay. So all of this I am teaching from Dennis Zill. You have shared the book, right? This is a good time to pause and recapitulate again what we have done so far. So we started off with the terminology of the differential equations. We talked about why they work in the physical world, how the physical world behaves. These differential equations are a manifestation, you know, and you solve them to find out the answers to your physical solutions. So we started off with the first order linear, then we went on to first order nonlinear, then we went on to solve higher degree equations, then we talked about the linear second order homogeneous differential equations. We found out the criteria to find out whether the solutions are linearly independent. We talked about why they are important. Then we have discussed today the non-homogeneous second order differential equations, and we have discussed two methods, one very briefly, the method of undetermined coefficients. We have also discussed the caveats over there, and finally we discussed the method of variation of parameters, and now we are going to talk about, and then we discussed a physical problem where everything, you know, comes in place. So now we talk about the Green's function. So I could have gone on and talk about Cauchy-Euler's equation, which is the only variable coefficient second order differential equation which can be solved using the substitution method. But I think in terms of continuity, we should first talk about the Green's function. So there are two kinds of problems that you can come across in second order differential equations. One is initial value problem and the other is the boundary value problem. So initial value, you understand that you have, geometrically speaking, you need to specify a point and take the slope, and that will help you determine the undetermined two parameter family of solutions C1 and C2. Okay. So first things first. So first I'll begin with the initial value problem, and then we will discuss Green's function for boundary value problems as well. Okay. All right. So we need to write something down. So y double dash plus p of x, y dash plus q of x, y is equal to f of x subjected to the initial value y of x naught is equal to y naught and y of dash x naught is equal to y1. This can be expressed as a superposition of two solutions which we have already proved as yc plus yp. Over here what we say that we can write this as a superposition of two solutions. What? First of all, we can write this thing down as y double dash plus p of x y dash plus q of x y is equal to 0 for y x naught is equal to y naught and y dash x naught is equal to y1, and the particular solution y double dash plus p of x y dash plus q of x y is equal to f of x corresponding to homogeneous initial value problem. Both are given to be 0 here. Okay. So this can be reduced, this is the claim that this can be reduced to two problems. One is this homogeneous differential equation with this initial value, and other is the non-homogeneous equation with these initial values, which are homogeneous, both going to 0. Okay. So Green's function. Over here as well. So what did we do? We said in method of variation of parameters that yp is equal to u1 of x y1 plus u2 of x y2, and we said that we can find the values by applying this. U1 dash of x is equal to minus y2 of x f of x over w, and u2 dash of x as y1 of x f of x over w. This is what we said. This is we already know. I've just shown you all this. Okay. All right. So now, if I just plug this thing back, what can I write? I can write this as yp is equal to y1 we will have some x naught to x minus y2 of t f of t divided by omega of t dt plus y2 times x naught to x y1 of t f of t divided by w of t dt. Okay, where you know that my w of t is y1 y2 y1 dash y2 dash determinant. जी क्यों? This is the dummy variable. Once you plug in the value, you will again, yeah, right? Are you familiar with this? That this is the solution that you need to obtain. So if you give these values, once you solve for this, you will eventually get the answer in x, right? Okay. So now I can write this as so I need to write it down as something which is okay. Yeah. So these are I can y1 and okay. Yeah, perfect. So this is y2 of t, this is y1 of t, this is y1 of x, this is y2 of x. Because I am integrating over t, I can bring it inside, so I will have x naught to x minus y1 of x, y2 of t, f of t divided by w of t dt plus x naught to x, y2 of x, y1 of t, f of t divided by w of t dt. Okay? Now if you can see, all these terms now, because they have the same limits multiplied by the same variable, so I can write this as yp is equal to x naught to x, y1 of t, y2 of x minus y1 of y1 of x, y2 of t divided by w of t, and this whole thing gets multiplied by f of t dt. This thing here we call as the Green's function. So this will be direct consequence of the method of variation of parameters. And now, if you put f of t equals to 0, immediately you see everything will be 0. So this thing doesn't exist for a homogeneous equation. The whole construct is such then that you ought to have a non-homogeneous ODE, and then you can construct a Green's function for it. Sorry. What else that you can make out of this? So now just have a look at the Green's function. The Green's function that I write here now tell me, what is it that you can conclude from here? And that is a very, very important thing. Pardon me? Wronskian has to be non-zero because you will have, for a second order differential equation, you will have two linearly independent solutions, sorry. Come on, guys. So I can of course write over here very, very important thing about Green's function. Look at the construction. Excellent. So if I give you a differential equation and I change input 1,000 times, the Green's function is not going to change. It stays the same provided your associated homogeneous part stays the same. So it has nothing to do with the forcing function. It is entirely constructed from the associated homogeneous part. So if you are given 5 equations with different inputs, as far as the Green's function is concerned, it stays the same. Okay? All right. Okay. So now that you understand this, we can go on and do an example. If you have any questions up till now, please ask. There is nothing new that we have done. It's just that we have constructed the Green's function using the already known knowledge from the method of variation of parameters. The tea has been served to you. It is maturing? Yeah. Some reference point. So if you, let's say, put x is equal to x naught, then it will be 0. Yeah, some value. Yeah. But you can do a to b, some interval you can define. It is defined on an interval, right? So that is the interval that you are talking about. So let's do an example. An initial value problem. Up till now, all that I've talked about is the Green's function for an initial value problem. For a boundary value problem, you remember that we have generalized boundary conditions. So we have to satisfy those, and for that we have to come up with some non-trivial changes that I'll do next time, not today. So very simple differential equation. Y double dash minus y is equal to 1 over x. Y1 is equal to 0 and y dash 1 is equal to 0. And in the other case, you have y double dash minus y is equal to e raised to power 2x. This is the first problem. And the second problem is y of 0 is 0 and y dash of 0 is equal to 0. Find the Green's function. This is very simple, right? Auxiliary equation will be m is equal to plus minus iota. So the Green's function will stay the same. The only thing that will change eventually is your solution that you write. Over here, the particular solution will of course change. So just find out. Oh, sorry, minus 1. Yeah, sorry, I'm sorry. Minus am. Thank you. Yeah. Yeah, because m square minus 1 y is equal to 0, m square is equal to 1, m is equal to plus minus 1. Thank you. Yeah. So you will have what? Y is equal to e raised to power c1 e raised to power x plus c2 e raised to power minus x. So once you have this, then of course you know already that y1 is equal to e raised to power x and y2 is equal to e raised to power minus x, and of course your Wronskian is y1 y2 y1 dash y2 dash. So the only thing that will change over here is that in this particular case it will become 1 over t, and in the other case it will become e raised to power same. Where does your x naught begin from? In this case you're at y is equal to 0 at x is equal to 1. So your x naught is 1. So it will go from 1 to x. And in the other case it is 0, so 0 to x. अगर आप x नहीं रखेंगे तो how will you integrate something which is integrated over 2 and you get it in x? That is essential. Okay. You want to write something without the c's, right? So you have to do a definite integral. It has to be a definite integral so that you can write it down. लेट्स से x माइनस टी है, कोई आपने उसको इंटीग्रेट करना है फ्रॉम लेट्स से 0 to x dt. So this will be whatever up, you can write e raised to power x, e raised to power minus t, you can take it out, and now when you do this and you apply it, so you will have to get x. So if you have no x, then how will you get that x? You know what I mean? It is simple, this is integration that you have to. Boundary value mein you will give a and b. Over here you don't do that, right? So you will make some changes also. So let's say a to b, you can go from a to x and then x to b. Over there you also do this, but of course then you will have to write down two Green's function and take into account both the boundary conditions. Okay, I think the time is up, so questions please ask. We can go now off here.